also reviews for some parts from this exact equation as well. So I will, for the first half of the class, I think I will just going on the exact equations, because I think some of you still not really familiar with the process. So I will just give you some steps and procedure. What would you do in the exact equations? Okay. Okay, and one more time, I'm reminding you that the homework, if you still want to submit the homework, although maybe it passed the deadline, you still can send me an email. Okay. Okay. Now let me start the lecture from this exact equations. Okay. So exact equations is if we have this kind of equation that has, let's say, a function of two variables x, y, and it has the dx and dy on both sides. Okay, so in the left side's equation, we said that it is an exact equation if all this stuffs, all this m and n, they are exact differentials, which means because we define the m and n as a function of two variables, we are going to define the exactness or the exactness if we differentiate this part of m with respect to y, and this n we differentiate partially with respect to x, and if they both have the same value or the same equations, we say that this equation will be exact. We can also say the m or n is actually our partial derivatives. Our partial derivative. We have the f, the capital F, the partial f, partial x. That is m. We can say that this is m. And partial f, partial y, this is n. So it's like when we did partial derivatives in calculus 1, we can easily derive, right? Partially we can easily derive. But now our goal, our objective is, from that result, we are going to reverse and going back to the original equation before it was derived. That is actually what this exact equation will do. Okay? Now let me rewrite this in more in a short summary in the next page. Okay? It will be the same thing. You can also add into your notes. So first, let me write the method of solution. So given m okay, we start with this. And we say that there's exists function of x, y, or maybe if you would like to make it the same with the previous one, maybe f with capital F like that, for which we define that the m is actually partial f, partial x is equal m. Okay. And from this statement, if we would like to get back to our original equation, which means our original equation is our f, right? Our f. So what we are going to do, we are going to integrate this, integrate both sides. So integrate both sides. Maybe let me just state through here. So integrate both sides. So we will have f. But of course, the assumptions that we have here is this function is having two variables x and y, right? So when we integrate this, we are going to have, for example, this m will be having an integrated form with respect to dx. So let me just write that first. Integrate m xy dx, okay? And it's actually plus a constant. But we need to define what constant that might appear on our function. Because remember, we differentiate partially to become this dou f dou x, or partial f partial x, right? So the function that will appear is actually function of y. So we can say that this g of y is the constant of integration with respect to dx. Now this is becoming more interesting, and this will confirm why we are having this function of y. Because in partial derivatives, like we did when we proved that this equation is exact, we proved that the partial derivative of this m with respect to dy and with respect to dx, they have the same value, right? They have the same value, that we call them exact. Which means when we have this f, let's say we just wrote this as maybe this is a function of y. But we can confirm. When we have this, and if we partially differentiate this with respect to y, it should be the same with the other part. Okay, that's the idea. That's the idea of this exact equation. So when we have here, then we are going to, maybe let me make some arrow here and write partially derive with respect to y. Then we will have dou f dou y, okay, and all the integrate this m and g will be integrated or will be derived with respect to y. So let's say we can write dou y of the integral m xy dx, okay, and maybe close the bracket, and this will be plus with g prime of y, because this is what we assume that maybe this is a function of y, okay? And this should be the same with our n. Okay, that's because we already proved that they are exact if they have the same value. So we need to have the same value of n here. So from these equations, we know that from this part here, we know that the n, okay, or maybe g prime, let me just write the results, g prime of y is equal n minus dou y, and then bracket the integrations m xy dx. Now, if we, let's just say we have this, and we know this is the G prime, and let's just say we are going to try to derive one more time with respect to x, just to see what is the correlation between all of these notions here. Okay. So this form here, okay, this form. Let's just try to partially derive with respect to x. And what will happen is we are going to have dou n, dou x, and then minus we can move out this partial of x going inside here to remove this x. Okay. So we are going to have dou y, and this is going to be inside here. Now, why we can do this? Why we can move this partial x inside here? Because no matter x or y, they will be the same value at the end, right? Partial. Remember from your calculus that when you have this partial yx, this will be equal partial xy, right? Okay, so no matter what, so I can say that, okay, we can just partially derive with x to remove this dx, okay, and to remove this integration. And what we have here is actually we will have this dou n dou x minus dou m dou y. Of course, if you look on this g prime y, if we differentiate, it will be 0 because we differentiate with respect to x. So we know that this is becoming equal to 0, which means that we are just seeing that, okay, we are going back that the exact equation will be available, or we can have exact equation if they both values have the exactness. Okay. Okay. If you would like to start from the other parts, okay, for example, this is we start from m. We can also use n, and this one will become x. And the result, when you try to elaborate, they will be the same result. Okay. So we can also check, let me write here, alternative. That the f, we can also use the n. But this will be dy, and this will be plus some function x. Let's say h. And the h prime, if you differentiate with respect to y, to x, sorry. This will be m, or maybe let me move a little bit to the left, and minus dou x, xy dy. So no matter part you are going to observe, as long as it is exact equation, you know the exactness, you can go through here or here. They will have the same result. So what is the solution actually? The solution is just this. So we are going to check, and then we check with the G prime here or the H prime, and then combine all together, and then we'll do solutions. Okay? I will go in the next example. Okay? This is to show where does the exactness comes from, and how do we prove that they are both this has the same value or the exact value. If you would like to take notes, you can take notes for a while. Is it too small? Maybe you need to zoom in. Maybe this big. This okay? Clear or need to bigger? Clear. Okay, I think this is a concept. Maybe it's a little bit abstract, but I think we have an example. Maybe it will be more practical, and we can see how we can solve the equations or the exact equations. Okay, let me go through some example. Okay, just to see how we can solve the equation. Let's say we start with the simple equations. Okay, let's say we are going to solve this. But I think you can solve this in separable, right? Do you think you can solve in separable equation? I think you can. But let's say we are going to solve this with exact equations. Okay, let's say. First thing is we define m and n. Okay, we define m and n. Let's say the m is this one, and n is this. Okay. Before we proceed with the process, we need to check whether the exactness. We check the exactness. Is it exact equation or not? To check, we can try to differentiate both with different. For the m, we check with partial y. With n, we check with partial x. Okay. Now we check. M is 2xy, so we are going to differentiate with respect to y. This will result to 2x, right? And for n, we also differentiate with respect to x. Okay, now they have the same result to x. Now we can say that equation is exact. So equation now we can proceed with the exact equations. Okay. We can start from m or we can start from n, no matter which path you follow, the results should be the same. Let's say we start from m first. Okay. Let's start from m, which means that this m is actually our function. Let's say we have the function that we are going to take as our solution. So we take that this partial f partial x is actually our m, or in our case here is 2xy, and our partial f partial y is our s squared minus 1. Okay. Now let's integrate. Let's just say we take the left path. Okay, we integrate with respect to x. Okay. Then we have f. Integrate to xy. We will have x squared y. X squared y. Let me write the constant in blue plus a constant g of y. Let's say we have g, or any functions, any symbols you want to write, but it will be a function of y. Okay, and then after we get this, then we derive. Why we derive? Because we need to make sure that it is going to be the same value as this. Okay? So we derive with respect to y. So we get this, go after y. Okay? So we derive, let me write here. This becomes 2, sorry, y, because it's y, so x squared, right? X squared plus this become g prime y. Now this part should be the same with this because of the exactness that we proved before. Okay? So conclusion here that the g prime y is -1. So the functions should be, if we integrate, so g of y should be -y. So our proposed solutions, proposed solution is we have f xy x squared y minus y. Or to be precise, that it can be equal with anything because we don't have the initial value, right? So we can actually have in many points, right? So maybe we can just state this is equal a constant. Okay, we can just state this is equal a constant c. So if we answer this, probably okay. This is the implicit solution because we have both x and y. If you want the explicit solution, also you can just factorize the y, and then that will be the explicit solution. I think up until here is okay. It's fine. And if you want to know what the c, maybe the question need to be added by the initial value. The initial value you can just plug into the equation, and then you can get your c. Maybe if you would like to try, maybe we can try trying from this x squared minus 1. We can try to make out the integrations. But we integrate with respect to y. Yes, correct. Then we will have the function of x. So x squared becomes x squared y. Okay, x squared y. Okay. So if you would like to try, we could also try that this will be x squared y minus y plus h of x. And then it's become, this will result in 2xy 0 and then plus h prime x, or maybe let me write with blue. And then this should be the same with the dou f dou x is, or m is 2xy. So the h prime x is 0. Now the h x is, it's either 0, well it can be also a constant, right? So the proposed solutions, well, both are okay because they make sense to our proposed solution. So the proposed solution from here, if we take another root, is x squared y minus y, and then if we take 0, then this is this solution, or if we take the constant, this is also plus c. But the constant is a constant, right? It can be any number. Then we can just say that x squared y minus y equal constant. It's the same structure with the our other solution that we had before. Remember that if you have the 0, when you have the h prime 0, which means that if you think to integrate that maybe there will be a constant, right? There will be a constant, or it's just 0, 0. Right? It can also possible to make a solution. Okay, let me give you one more example. You can try to tackle the example, and then after that, we go to another form in exact equations. Okay, another form. Maybe before that, any question from here? Any question from here? Any questions? Okay. So the first part, check the exactness. Next one is you can follow from the m or n, try to find your proposed f, and then after that derive one more time with other variables, and then check with the other part of the equation. So if you try from m, then later you need to make sure that it's the same form with the n when you derive partially. So either from m or n, go find the f, and then differentiate partially. Make sure it's the same with the m or n. Okay, let me give you another example. And then you have, let me give you initial value. Okay, let me just give you some maybe 2-3 minutes or maybe 5 minutes to try this. Maybe you can check if you can solve with other method as well. But this is, of course, will be possible through exact equation. If you want to try maybe another method, that maybe okay. But I think if you try This separable, I think no, right? Yeah, I think no. The linear equation also no. So yeah. Or if you want to draw with your GeoGebra, okay. I think in your homework there are some parts that need to be drawn. You can draw using GeoGebra and click digitally and something. If you want to draw by hand, that's also okay. Yeah. Maybe change the time or density if you do something more, more clear. And you can maybe predict which will occur. And then just take the points, right? Take the points, the 0, 1. Right? And maybe this one. Yeah, perhaps it will be asymptotic. Jadi bikin sama kayak yang sebelumnya itu. The first thing is you need to check the structure, and if you want to make it clearly its exact equation, maybe you need to rewrite the form in terms of m dx and dy, right? Maybe let me help you with the first structure that we can have is okay, and then perhaps we are going to move into one side, and this negative 2x negative y is become 2x plus y, right? So you can see clearly that this is can be rewrite as the structure in the exact equations. And don't forget, after we write this exact, although it seems like exact equation, but we need to check the exactness. Every time you have exact equation, check the exactness first. Because sometimes there will be like, it's not exact, but in the next part after this, I will try to explain. If we have the structure that almost exact, we can do something about it. So if there is like almost exact, we can do something about it. So we can make it into let's say we force out the equation to be exact. But let's say we try this, and I think this will be exact. You can see this 2x plus y and x minus 1. They both, if we partially differentiate with y and x, this will be equal to 1. Right? Y is 1, right? X is 1. Right? Okay. So we can check the exactness first. And take note that this m, right? This is n, right? So we take the partial y of the 2x plus y. This will be 1. And take the partial x for x minus 1. This is also 1. So from here we got the results that this is exact equations. And to write the solutions, we can try from m or n, whatever path you choose. Okay, it should be the same at the end. Let's say maybe the first one is from m. Okay. Let's say we get the m here. So let's write that the dou f dou x is 2x plus y. So integrate, but with respect to the x, this will be f x squared plus xy, and then we generate a constant of a function y. And then after we get this, we try to partially derive with y and try to confirm this result with the n. Okay? This will be 0, 0, this will be x, right? So x plus g prime of y. Now we have the n, or dou f dou y is x minus 1. So from this n, we get the conclusions that the g prime y should be negative 1, which resulted in g of y, maybe this, g of y is negative y. Then our proposed solution, so proposed solution, or proposed curve or proposed function is f x squared plus xy minus y. Okay. Now to prove that this is our confirmation are okay and correct, we can also check with the other path as well. We can check from the end. Okay. So we can check from here also. We integrate with respect to y. So we get that the f is xy minus y plus h of x, and then we partially derive. Well, of course, if you are convinced and sure that this is your proposed solution, you can just use one way. But if you want to like check the other solutions, you can check whether maybe there will be something missing in your calculations. Okay? So this is just, let me write this is alternative. Okay, alternative that you can do. So this will be y and then plus h prime of x. So from our m, the h prime is actually 2x, and h of x is supposed to be x squared. So also the same, that the proposed solution from here is the x squared plus xy minus y. But I think to avoid some miscalculations, sometimes if you feel you are comfortable with just one fact here, just focus on here. Because sometimes maybe you're missing this too, and maybe different conclusions will be. This is my suggestion. But if you are, you have convinced that, okay, I think both are okay. Okay, now this is proposed solution, but I think we have the initial value, right? So we have to check the initial value, this 0, 1. So check, so this initial value here. So we are going to check 0, 1. That is going to be 0, 0, and -1. So this should be -1. So x squared plus xy minus y, this is equal to -1. Or if you want to solve in more precise, explicit, so we can write in explicit form if you would like. So xy, so y, x minus 1, and let me move the x squared to the right side. So you get the y is, this is x minus 1. So you have this explicit solution. And remember that at the beginning, I forgot to mention that the proposed solution, the f, the capital F, is always in form of this. Okay, this function should be equal to constant. Because remember, I think in calculus 2, and I think calculus 1 also, I think calculus 2, when we have this function of 2 variables, when we have this equal a constant, remember that we can make a graph, like you have a map and you have like a contour, like the mountain. We can write something similar to this. The function, the x, y, and then it's a constant. So for every constant, they will be having different height, probably. Like for example, and maybe you have a red color here. Maybe red is giving you more like highest, probably. But this is going to have the same or similar structure with our function here. It's equal to a constant. Okay. Now there is another part, okay, in these exact equations that I have mentioned before, that we might have something that is similar to exact equation, but it's not exact equation, which means the m and n, when we partially differentiate, we differentiate, it's not the same, so it's not exact. But we can make those equations to be exact. Okay? So let me write here. Maybe let me write in the next page. Okay. So let me write recall that the form for the exact equations is this. Okay. Now let me write if the equation above is not exact. Which means that the dou m dou y is not the same dou x. Then we can multiply them with integrating factor. Let's say mu, integrating factor mu. So the equation comes, let's say m okay, we can have a break. Okay, we can have a break and continue this part. Okay.
Professor, for the last question for the homework, can I switch the y and x for the general form? jadi ini tukar gitu. Kan general form dari general source ini kayak gini kan. Nah, cuman ya kalau ikutin form ini jelek banget gitu. Susah banget. Terus
bisa aja sih.
Bisa, boleh.
Bisa aja. Bisa aja.
Bisa.
Okay. Well, let's go back to this. Let's say this is almost exact equation, and we want these equations to be exact. So first thing is I'm writing here that we are going to have integrating factor mu, and we are going to multiply all the elements with this mu. So when we multiply, then we need to have another criterion, right? Another criterion that we need to confirm that this new equation is exact. So we are doing the same thing as before. Check the exactness, blah blah blah, right? Okay, so we need to make sure that this criterion. Suppose this is exact, then criteria for this equation to be exact is, because now we have mu, then we are going to include mu m, and this is the y. This is supposed to be equal with the x for the n, mu n. Okay. So because mu is a functions, it can be x, it can be xy, it can be y. For now, let's just assume they are functions, that we are going to have a product rule with these two partials. Okay. So we are going to have mu and then m with subscript y, which means this is partial y. Okay, remember in your calculus we can also write like this, or maybe let me write bigger. Okay, and then plus product rule, mu y and then m. Same thing on the right side. We are going to multiply mu with n x and then plus mu x and then n. Okay, and then we try to let's just rewrite and maybe simplify grouping all the mu together. So let's group the mu here and here. Let's go right on the right side. So mu, or maybe let me write mu in blue to make it clear. So let's move nx to the left. It will be my minus nx. So this will be mu x n plus or minus now, sorry, minus mu y m. Okay. So m n and then my and x, they are all known functions, right? We know the functions because we identify the beginning. Now the problem in our equation now, okay, to make our conclusions is basically our mu. What is mu actually? Because it has all this element here. So to simplify the equations, we need to assume, okay, mu is function of one variable, and we need to assume that mu is function of one variable. Why is that? Because if mu is function of one variable, either x or y, we can remove either this part or this part, and then we can simplify. The mu becomes something here that is the integrating factor that we want to multiply. Okay, so let me just give you an example here. So assumption, or assume the mu is a function of one variable. So it can be x or y. So case 1, if mu depends on the x, let's say it's a function of x. So this mu partial y will be 0, right? Because it only depends on x. So we can say that we can remove this, and we can rewrite this in terms of, let me write the mu x, then becomes, we can write this as d dx of mu, right? That is equal to my minus nx bracket mu divided by n. This is the first case. The second case, similar. We are going to make the mu x 0. So we will have this negative here. So the second case, if mu depends on only y. So mu y, or now this is supposed to be negative, okay? It's negative mu, but I will multiply negative, so I will have nx minus my divide by, now divide by m. So from these two, we are not done yet. Remember the integrating factor in the linear differential equation? We need to write like that. So e to the power of something. So we are going to write this conclude that the integrating factor let's say if mu is function of x, then equal e with power my minus nx over n dx. Now for the function of y, we can write nx minus my divided by m dy, or we can make it e to make it has the same structure, so you don't really need to memorize another formula. Let me just take negative and then write the my minus nx divided by m dy. Okay. Okay, now the problem, how to define the case 1 and case 2, it practically depends on the equation. So you need to maybe having a little bit trial, which one that has the, like when you try this, my minus nx over n or nx minus my over m, which one is getting more defined result? Maybe getting the result of a function of x or a function of y. Then that will be your choice. Okay? For example, if you define that I get function of y, so I need to have dy. So probably this will be okay. But you need to make sure and trial some these two cases. Okay? I think I can give you some examples to check how to use this case. Okay, let me give you example. Okay. So example. So let's see, we have xy dx plus 2x squared plus 3y squared minus 20 dy. Okay. As usual, you can check the exactness And I think, of course, it will not be exact by a simple differentiation. You will see that it's not the same value when you partially derive. Okay. So partial y become x, and partial x it become 4x. So not equal, right? So you can check first is to check this, and this will be x, and then the other part is this. So we have 4x. So we say that it's not exact, right? Not exact. But then now, because we know how to deal with the integrating factor to multiply this equation to be exact, so we can try to have some trial. Okay. Maybe let me rename this m n to make sure we have the same structure. What we have in the equations is partial y. It's actually my, right? My. So we can also write the m partial y like this is x, right? And this is n x is 4x. Well, if you maybe let me go through the equation here. It's always started with my minus nx or nx minus my. So either equations, they will always start with this. So we can actually guess from the results. Okay? For example, we have this x. Okay? Then it's either my minus nx or nx minus my, but we need to know which denominator we are going to get, m or n. We have m is xy and n is that equation. So probably the best way to choose is m. Okay, the best way to choose is m. So let's make this my minus nx divided by m. So that we have x minus 4x divided xy. And the result is negative 3x over xy or negative 3 over y. So if we define this by m, and of course this can be mx or minus my or my minus mx, it's okay because if we look at the integrating factor, we can just always plus the negative when we deal with d1. Okay? So this is more practical. So doesn't really matter nx minus my or my minus nx. I think you can just stick on my minus nx, and later you can just multiply negative if it's d1. Okay? Okay? It's more practical. So because it's divided by m, so we are going to have the function of y for the integrating factor. So we are going to have the integrating factor function y. Then we are going to have the e, and then with power of negative 3 over y dy. And then we can solve this first. We have 3 1 over y dy, or this is e 3 ln y, or e ln y cubed, and this is y cubed, right? It's canceling this. Okay, we're not finished yet. So we propose the integrating factor as y with power of 3 or y cubed. So now we are going to multiply the solution or the equation with this y cubed as our integrating factor. Okay. So maybe so first, always identify m and n, right? Check exactness. If not exact, find the integrating factor mu. Multiply equation with the integrating factor and then solve the exact equation. Okay, now we would multiply our equation. Maybe let me just copy. This and copy there. And then we multiply with y cubed. So y cubed, y cubed. Okay, now we have x, y with power of 4, dx. And then let's just multiply y cubed inside. This will be 2x squared y cubed plus 3y5 minus 20y cubed dy. And then again, we try to make sure that this is exact by take the partial derivative. So taking the m, this will be 4xy cubed, right? And take the other part. Okay, this is quite long, so we need to write exactly. But since it's partial with respect to x, so we only have the front equation here, which means it's 4x y cubed, and it's exact. So it's now exact, okay? It's now exact. Now this is exact equation, which means we can continue our solution, okay? Continue our process. Either you choose the m or n, doesn't matter. It should be the same results. So we are going to have, let's say, proposed solutions, fxy. We are going to integrate the xy with power of 4. This will be half x squared, right? Half x squared y power of 4, and then we have another function g of y. And then similarly, we are going to derive this f with respect to y. So we have 2x squared y cubed plus g prime y. And you see that we have the same structure, right? 2x cubed squared and y cubed. So g prime will be this whole equation, 3y with power of 5 and so on. So this part will be, let me just write with the arrow here to show you that is equal with this. So g prime y is with that. So check the integral. So this will be over 6, right? Over 6 is half. and over 4 is 5, and perhaps this is our proposed solutions. So we are going to have the proposed solution plus half y power of 6 minus 5y power of 4. Or if you would like to write equal constant, this is also okay. I think if you want, you can check the other part with n if you want, okay? With the function of x. Okay, I think I'll give you another example. I will give you another example so you can try again. And then that's it for today. And we have feedback. The Thursday class for this week, I will focus on maybe some notes on your homework, and then maybe a little bit review if you have time. And next week, on Tuesday, we move to the substitutions after exact equation. And Thursday, maybe review for maybe either exact or substitutions. And next 2 weeks from now, the Thursday class will be a quiz. Okay, so the component will be the first chapter, the introductions, the slope fields, autonomous order, the first order techniques, the separable, linear, exact, etc. Okay. I think up until the substitutions. I think. Okay. I think let me give you one more example here, and then I will see whether you are able to solve. Okay. So solve. So I think the difficulty of the course, this engineering of math, is basically first difficulty on techniques in calculus, because we need some of the techniques. So if the techniques becomes more and more complicated, then I think difficulty will be more also increasing. So you need to review that part. Some techniques from calculus 1 or 2, like the partials, the integrations, okay? And I hope you get more familiar with those techniques. Because I think the idea on most of the techniques in engineering of math, they are based on what we have in calculus. Oh, yeah. Remember, you need to make this structure with m and n, with dx and dy. I think probably okay, just multiply with the x, so you have the x here. Same thing because it's 0. So first is the structure, and then second, check the exactness. Okay? Check the exactness, and if not exact, and it's obvious it's not exact. If you did non-exact one, but almost exact, and then you need to find the integrating factor. To find the integrating factor, it's a little bit tricky because it depends on the results on your the partial. Right? If the partial resulting in maybe y, probably you need to find the denominator, maybe m or n. Yeah, you could try and imagine. Maybe you could try both one. Which one is more logical and easier to be found? Yeah, firstly, we can maybe write as this. And then check the exactness. Okay, how to differentiate this? Maybe we can separate. So we are going to separate both sides. Become this and this. But since this is function of x, right? This x variable, so we could compute the 0. Right? So we could just differentiate this one. Okay, this is a constant. Right? So 2y over x plus 1. Okay, now the other is the x of 2y, which is 0. And of course, from this particular my and nx, okay, this is, if you forget that this is my, this is nx, partial m partial y and partial x. So it's not the same, so we know that it's not exact. Then we need to choose, okay. Let's just begin with the my minus nx. This is equal to 2y over x plus 1. And we need to divide this with either m or n. So we could see from our m or n, we could try both if you would like to compare. If we try this left one, we end up with the 2y, and then we have x squared and plus y squared, right? So it doesn't really have a good structure or a good integrating factor if we would like to use that in our solution, because we assume, remember, our assumption is integrating factor should be one variable. So we need to make this into one variable only. So let's say we are going to use 2y, and I think if we use 2y, we are going to have this a function of x. Okay? So we are going to divide this with n. So we divide with 2y, which means that we are canceling this, and we have 1 over x plus 1. Which means we are going to have the integrating factor as a function of x. So we could write the integrating factor as the e, right? And then just as usual, 1 over x plus 1 dx. And this is equal to e, this becomes ln x plus 1. Or we could just say that this is going to be x plus 1. because we are sure that it should be a positive. Because at the end I get the x plus 1 as the integrating factor. Like what you did, right? Okay, good point. Okay, actually. Okay, did a good job. So actually, if we multiply this with x plus 1, we will get the exact equation if we multiply. So what do I mean by this solution here is, at the end is we get the integrating factor is x plus 1, which we are going to multiply. But actually, if you think, like, because you have the equaling 0, so perhaps you need to multiply it with x plus 1, and maybe you will get your exact equation. So I think that is what we are doing, okay? What we are doing. So actually, we are not really necessary to do this integrating factor, okay? Okay. The integrating factor is actually we need to find some components that need to be multiplied so that this equation to be exact. And it's right in front of our equation, right? So this is our multiplication factor. Okay? You get the idea? This is to show that, okay, the official integrating factor, this is we need to multiply. But actually, if you think at this equation, I probably just simplify this and maybe multiply with x plus 1 and we have the exact equation. That's also okay. That's good thinking. So this is actually our integrating factor. Okay, I think the rest you can solve the exact equations, okay? Okay, I think because now it's already 2:55, we can move on to our feedback. Just 2 questions about the exact equations. Okay, I hope you don't mind. Okay, so I can know which part that we need to evaluate and review. Okay, let me go through. Wait.